and we looked at one example from cellular communications as to how we might use the concept of the energy of a signal in practice. In this video, I'm going to give you another example. This time, the signal x of t of interest is not necessarily a voltage waveform. The point I want to make is that even though we motivated the notion of energy by thinking of x of t as a voltage waveform applied to a resistor, even though the idea of energy may have originated by thinking of it as the amount of energy dissipated in a resistor, in electrical engineering these days, we are often interested in signals that are not really voltage waveforms. And the same idea or the same definition of energy is actually used to measure how large a signal is. So really we use this not just to physically mean the energy dissipated in something, but just as a measure of how big a signal is. And if that's a little bit abstract, so let me give you an example. So let us say that we're trying to build a robot, and you want the robot to do a certain maneuver, and let's say we want the robot to be in a certain position at a certain time, and let's say that this is our desired signal x of t. So notice that x of t is not necessarily a voltage waveform now. So what x of t represents is the position of a robot as a function of time. And in this example, this is what you want it to be. And let's say we have two different algorithms that try to maneuver the robot. And let's say one of them gives you the position as a function of time given by this magenta line. And let's say the other algorithm, maybe does something like this. And the question is, which of these two algorithms is better, or which one should we pick? And if you want to think about this problem, what you want to do is to be able to come up with a way to quantify which of these two algorithms results in smaller error. So you can see that we can define an error signal E1, let us say, as the difference between what we want the position of the robot to be minus what it actually is from algorithm 1. And notice that it's a function of time. So the error is different at different points in time. So the error itself is actually a signal. Similarly, we have another error signal for algorithm 2. Right? Now, which of these two is better? And you can think of these two error signals as approximation errors. Right? We're trying to approximate x of t by something else. And the algorithm, so we need a way to quantify which of these two is actually has smaller error. And for that, we need a way to convert these signals into a real number using which you can pick which of the two has smaller error. And here the notion of energy comes in handy. So what we can do is we compute the energy in the error signal 1, which will be given by the integral of the magnitude of E1 from negative infinity to positive infinity. And now we could pick whichever of these two quantities is smaller as the one that gives you the better approximation. Right? And this is a very useful idea in many areas in engineering. In many areas of engineering, we are either trying to approximate one function using other functions, or we are trying to predict one function using some information that we have, and you often want to know which algorithm gives you a better prediction. And quite often, your algorithm has some tunable parameters, and what you want to do is to pick these parameters in a way that the error is minimized. But since the error itself is a signal, what we would often do is say that we compute the energy in the error, and we will pick these parameters in a way that the energy in the error is minimized. In mathematics, this energy, the way we defined this is called as the norm of a signal. This is called as the Euclidean norm of the signal E1 of t. And there are many ways to measure the error. This is one way to measure the error, but this turns out to have many desirable properties, and it's quite commonly used in engineering.